and it will be my pleasure to discuss with you today the Mooney regulator line, most specifically the flow grid and the Flow Max regulators. There is a third line that occasionally will come into play in gas applications. It's called the Flex Flow line. It's a axial flow design. It plays much more in the liquid applications more than these two. So I'm really not going to address that so much in our discussion today unless someone has questions about it. So the first part of it will be the discussion really about the flow grid and get into its characteristics, basically the things that you have to know when you're speccing it, as far as the variations of the build to get it to do different things. And if we want to get into the, things like how the valves are, spaced during, placement of sense lines and things like that, we can definitely get into that. I definitely want to offer an opportunity to discuss sizing with you on both the flow grid and the flow max. And I think piping on the flow max needs to be part of that conversation because it'll be less familiar to people. But then we'll probably take a break after get to a point probably through the flow grid and maybe before the flow max, I don't know. And when we come back again, thinking about, we'll go for about an hour and a half the first go. I want to also introduce the Flow Safe line, which is another product line we stock of relief valves. Obviously, you can use a flow grid as a relief, or a flow max as a wonderful relief. If you're looking for something that's a simple standalone reliable device, then that's a good a good thing to have. So we'll talk about those and sizing of those. And at some point after I'm done with all of that and we've discussed any issues like troubleshooting you want to talk about or anything else you have on your plate, I will transition over to William Boger, and he's going to talk about the ultrasonic line, the Zic ultrasonics with you. So that's kind of the game plan. And if anybody has an agenda that you feel would help you from what we're talking about today, then I will shift it in whatever direction you so desire. I've created a madhouse of regulators around me here, so we've got a bunch of stuff to play with in case something dives off in a different direction. Drew can show you all the cleanup I'm going to have to do afterwards. So plenty of stuff here to discuss, and we can even tear down. If we can look at this board up here real quick, and maybe can you pan that in so they can see it? I put some information up here which I thought might be helpful. A lot of the documents on any of this stuff is obviously easy to access through our website, kgmgas.com. This is my information in case you need to ever address anything to me. We're always here to support you, whether it's doing, sizing, in specific applications or discussing sizing. Obviously, if you have any troubleshooting concerns on a particular product, things just, you're not clear on, please give us a shout and we will help you. And we help the technicians in the field. They can call up, and if they're having a problem, we'll help them land the plane, so to speak. So that's something we love to do. So my email address is up here, and the phone number here to our office. If you dial that number, we all share it. So it could be one of my cohorts, Casey or Nate or Dave, that answer the phone. But if you want to talk to me, just ask for me. And then these two websites, I think if you don't already have them, will be helpful to you moving forward, including we're discussing them today. Baker Hughes, which now owns the Mooney line, has a program called ValSpeQ. And Valspec covers Mooney, Becker, and a rotary control valve line called Mason-Elin. So they consolidated all their sizing opportunities into one program that you select basically the type of product that you're trying to size. And that website is up here for you. And then when we get to the FlowSafe stuff, FlowSafe has the same thing for their relief valves, and I put that link up here as well. So is anybody having any trouble reading that because of the lights? Maybe I can fix some of the glare.
I've also added those to the chat. If you guys can find the chat at the bottom of your screen, all of those links and everything you just talked about is going to be in that chat.
That help? Looking at the glare? Yeah. Okay. All right. So on into the flow grid line. A little bit of just the variety, wondrous variety of flow grid, of which if you ever want to come visit us, because we're not too far away, we'd be happy to show you about $4 million in flow grid inventory. We maintain basically all the body sizes through 8-inch here, which start with 1-inch NPT, 1-inch socket weld, that variety. And then that 1-inch throttling area moves up into a body size that has a 1-inch throttling area and 2-inch connections, flange connections, or NPT connections. So from there, it basically moves up to the 8-inch variety, which we stock all the 8-inch Mooney valves. And then when you go to the 10 and the 12, we don't typically have those in stock, but they're dual ports. They're the only dual port Mooney regulators that are kind of left in current production. You may have some like 2-inch dual ports or 4-inch dual ports out there in your in your sets. There's no problem with maintaining them, but probably if they haven't already been like the 2-inch version, if it hasn't been converted over to a large port, then we'll need to discuss that so that it's clear when it comes to the 2-inch stuff. If it's out there in the field and it was a standard port flow grid, the bodies are identical to the large ports, but there are some components that need to be converted so you can keep the soft goods current in those, because they won't be offering the standard port soft goods. So a little bit then about what a flow grid is and can do. It's carbon steel body rated 1,480 pounds in every size. It basically then is just a matter of the end connections that determine where it's appropriate to be set. Obviously this one, that's a 2x1 Mooney with a 150 class flange connections on it. So it's going into a 2-inch 150 class set. And that sets the model number with a flow grid. So if you know the end connections and you know the throttling area size, so like 1-inch here, 2-inch on this regulator with a slam shut on it, that helps you to quickly identify the model. And then the other parts of the build that you spec are its throttle plate and its diaphragm, because those are two critical variations or variables in getting something that'll perform the way that you want it to perform. So as an example here, this is an FG29. It's a 2-inch large port. Let's just say for the sake of our discussion that it has 100% throttle plate in it and a 75 durometer diaphragm. It's going to be basically set so that it's regulating 50 PSI, so that it has a spring that has a range of 25 to 90 in it. It has its restrictor, which is required. We'll talk about why you always have to have a restrictor. And it has a pilot filter to protect the small spaces in what essentially is the brain of this thing, the amplification chamber that with small changes in the pilot cause immediate and massive changes in what the body can do. It's, you know, a master blaster type situation, which basically gives it speed and accuracy that would be not possible, you know, in another arrangement. So, you know, we're speccing all those in and it becomes a model number. So as an example, in this particular case, the model number would be an FG29, which calls 2-inch large port with 150 class flange connections, 100 for the throttle plate, 75 for the durometer of the diaphragm. And if it doesn't have a V here, which is another variation, it's assumed it's nitrile because that would mean Viton. So that's the body part. And then it can't work by itself. So it has to have a pilot. That pilot model goes next in the identifier. FP7 calls it out as a brass pilot with that blue spring. Then the restrictor, which is a type 24 restrictor, which is stainless steel. And again, we can address why that's necessary. It has a pilot filter, which is the type 30 stainless steel with a drain, and it's mounted on the side. So the side mounting is like you see here. The two body ports that are being utilized, since it's already established that this is the direction of flow, which has to basically be determined by what's on top of the body, because the body doesn't care. Knowing that this is the inlet, that's where my pilot filter went. Then I've got my outlet where the gas is going to dump off the top of the regulator, where my pilot is mounted. So that's the C mounting configuration. If you pan over here, Drew, so here's another Mooney regulator. This one happens to have 300 class 2-inch flange connections, so it changes the model number to FG30, same throttling area, etc. But you see that the pilot is mounted on top in this case. That would be considered the mounting position A, okay? And we typically don't spec or configure them that way because we like this for its technician-friendly setup. Because in a situation like this, all the technician, you have your sense line run downstream, all the technician has to do is remove the loading line, take the cap screw to get access to the body, and they can do all their maintenance and inspections and stuff in the body. So, you know, it's this easy, just a couple of parts and I'm in there to do my maintenance, and then I can put her back together and move on. With this, I have to remove my outlet line, I have to remove my inlet line, I have to remove my sense line, because the pilot and the restrictor and everything's going to come off with the spring case. So it's more to get off, more to put on. And really I guess the trade-off is why you would do something like that is, let's say you have a space constraint. You have some very tight, you know, not very much room around the pipe where that regulator is going to be. And so you don't want stuff hanging off the side. So you want the pilot up top. It's a little bit of a challenge though, because if you are going to use that inlet port for the pilot filter directly mounted, it's really not something that you're going to get that space from anyway. You're probably going to have to perhaps use another filter, pole mount it like this Welker filter, and run your tubing to and from it to get the component away from where it's constrained. Take a ride. I'm gonna get finished taking this off so we can kind of talk about those individual components real briefly. Okay. So how it's functioning, flip this up. You can see that basically I have an identical, basically mirror image, inlet to outlet with a wall in the middle. And so the name of the game with the flow grid is I've got gas that wants to come in, whatever I decide is the inlet, try to cross over that wall and go to the downstream. So it's the things that I put on top of it that are going to determine its capacity, its ability to control as far as rangeability, its temperature range. Those kind of things will kind of be determined by the things that I stick on top. Typically, it'll have an O-ring wherever I don't want the gas to escape to. So I have a O-ring here, D model O-ring, D-shape O-ring, because I'm going to put a throttle plate on top of that. So in this situation, then I have the gas wanting to make that trip through the valve. Some of the gas is going to come through this pilot filter right here, and it's going to go through this restrictor, straight through the pilot, and with that loading line that I took off, it's going to load right on top of the spring case, on top of the diaphragm. So I'll have that throttle plate sitting in there that the gas now has to pass up and through, and I have a diaphragm on top of it, which is going to have gas when it's basically in its natural closed state, with the inlet pressure on top of it coming in from that pass through the pilot. So it's going to be up to the pilot to actually decide when that gas that's on top here, aided by this accordion style mainspring, valve opening in this kind of direction, and then close back against the throttle plate, when that gas can come off of that, the top of that spring case, and let the valve open. When it does that, the pilot dumps the gas coming off the top through this outlet port, and it rejoins the gas that's coming through going downstream. And until the pilot senses through its sense line that pressure has reached the desired set point, it's going to let that flow through. When it reaches a set point, the pressure from the downstream pressure is going to work against the pilot spring, close a little plug and stem against an orifice inside the pilot, block off this path to let gas dump. And the constant process that we talked about with gas coming through the filter, through the restrictor, through the pilot filter, will immediately reload it and close the valve. So it's a balance of forces that occurs within the pilot that literally the plug and stem moves about 1/8 of an inch at the most, between a 1/16 and 1/8 of an inch. And it is that movement of that small amount that can make the difference of a couple 100,000 cubic feet an hour flowing through the valve or being bubble tight shut off. So it's an unloading design. And getting to what this restrictor does, it's basically a small valve in itself. It has we'll get one here, take it apart. It has a little rotor that has a slot, graduated slot, that is cut into it. And see that. As it's turned, because there's a dial on this, you can set that, the amount of gas that can flow through that restrictor to a greater number or a bigger amount or to a lesser amount. And that gives you some flexibility with this valve to make it either more stable or more sensitive. So if you had it on, let's say, a real small number, you might do that because you want the valve to open as quickly as possible, knowing that gas is constantly coming through this, even when the pilot wants to dump gas off the top. But the pilot, when it does that, is always going to be able to do that quicker than the gas that can come through the restrictor. But if I put this on a really small number and make that amount that's coming through there smaller, it's basically going to interfere with the pilot dumping that gas off the top less. And so there'll be a much quicker evacuation, if you will, of that pressure on top. If I put it on a bigger number, then it's constantly trying to reload that. And when the pilot says to, dump gas off the top, because it's got more gas it's working against that's trying to reload, it'll open slower. One of the reasons you might do it, if you're thinking about, well, why would I want the valve to open slower? You can think about the relationship between another valve and maybe the two fighting each other, or in a situation where I want to make sure that when I reach my set point downstream, that this valve closes as quickly as it possibly can. Well, if I give that restrictor more gas that it's constantly loading on top, as soon as the pilot stops dumping, it's going to lock this up quicker. So you can use that restrictor as kind of a way to adjust that either sensitivity or stability of the valve. Okay. Now onto the throttle plate stuff. We're talking about setting capacity and setting turn down. With this particular valve, and this one that's listed in here, it has its capacity listed on the valve at the bottom. Let's see if I can show you here. See how it says 50 SD. It has step drill hole between the closest places to that center divider. You can see it's nozzle down in there. In the back side, you can see even better because they're smaller on the underside. What that gives this valve the capability of doing is at really low flows where the diaphragm is just peeling to expose just the first layer, first row of those. On the downstream edges where the control is occurring, it is giving you much tighter low flow control. This is what gives this valve with that type of throttle plate design a 300-to-1 or better than 300-to-1 turn down. It can use, and oftentimes in like a 150 class set, slotted style capacity plates. This one's a 100% slotted plate. So when you have one that you want to reduce the capacity of, it will have, it looks like it starts out like 100% plate, but then it has restrictions welded into certain places on it to give it an overall 50% capacity. Of the two that I just showed you, this one and this one that both say 50, they have the same top end capacity, but what changes is that turn down capability. Whereas the slotted plate with the reduced capacity or throughput because of the welded bars has about a 150 to 1 turn down. The step drill hole is double that. So you'll see oftentimes the step drill hole valves being used in 600 class applications, mainly. Like if you get a 600 class valve, it's going to be in there. You don't see them as much in 150 class unless there is a huge rangeability requirement. You have a lot of high flow demand, and then at certain times it's pilot loads. This is a regulator that can handle both of those like nothing else on the market. So you might use it in those instances. When I would avoid it, if I'm speccing it, is if I have low differential. Because, I mean, let's face it, if you had infinite turn down, that would mean that it would really be hard, if ever, to get the valve to truly lock up, because it's the smallest amount of differential pressure and it's wanting to give you flow creeping over that center median. So that's typically why this step drill hole isn't spec'd in the 150 class regulators, and quite frankly, they're more expensive. They're harder, they're more expensive to make, and they're one of the big like cost adders of what the total price of a valve is. So those kind of reasons are kind of taken into effect. But another thing I didn't mention about the step drill hole that is nice when you got those high pressures, therefore high velocities passing through, is to take that velocity away from the downstream edge of this, because that's where the wear is going to occur on the underside. It's the downstream edge where all that gas is being throttled. In those instances, having that gas actually not running at highest velocity across the surface of the throttle plate and under the diaphragm, but down into the nozzle. So it's going to increase the life of the diaphragms and reduce the overall maintenance requirement. So you'll get some of that initial investment back. So basically, like in the 2-inch model I'm talking about, that gives me 9 plates that I actually select from for determining which one's the right one for this job. 100% slotted, 100% drill, 75, 75, 50, 50, 35, 35. And additionally, there's a 25% step drill hole plate that's been created because of this whole need for people to have to convert over their standard port 2-inch to large port. And the standard port 2-inch with a 35% plate in it has a gas sizing coefficient of 380. So, oftentimes you're in a situation when you're trying to convert a valve like this, and you've got one that the top components are going to give it 25% more capacity or 20% more capacity. You may have a relief downstream, and you don't want that added capacity because it affects, now you have to do something with another component. So Drew, can you bring up that that capacity chart and share it with them? We have something which is a real handy tool to identify these gas sizing coefficients by model number. So we can take a look at that real quick, and he's going to basically make sure you have this so you can get it. And also, if for whatever reason that doesn't work, all you got to do is just email me and I'll email you one back. This basically will give you, when you look at the body size, the number of ports, which the ones where it says dual port and it's not a 10-inch or a 12-inch are obsolete. But hey, you might have them in the field and you might have to do something with them, so it's still good information. But it'll tell you, obviously, going across from left to right, the body size, the number of ports, the types of connections available for that particular group. And that sets the model number. So like when I was mentioning before, the FG29, if you go down 6 rows, you'll see the 2-inch large single ports. And if you go across on the 150 RF flanged, you'll see that that makes it a model FG29. Okay, so then when we decide what throttle plate's going to be in it, it gives us flow factors to consider based on each throttle plate. It gives us the gas sizing coefficient. It gives us the CV, so essentially the liquid sizing coefficient, and it gives us the C1, the valve recovery coefficient, which is essentially literally the CG divided by the CV. So we're concerned because we're regulating gas here. We're going to focus on the CG, and if it had a 100% plate in it, that gas sizing coefficient will be 1420. Now we can plug it into Valspec here later, but there is a simplified gas sizing coefficient just to get basically a thumb rule scientific estimate of what valve will work for certain process conditions. And that essentially is if I know my maximum flow rate, Q max, and I divide Q max by my inlet pressure, it's going to give me a idea of what the required CG for that job will be. Obviously, Valspec gives us a lot more because there's obviously changes in capacity as the inlet pressure varies from the downstream set point. In other words, more differential pressure. The more the differential pressure, the more capacity. It'll reach sonic velocity and they'll basically increase the capacity further. So those aren't really accounted for or accommodated by that simplified gas sizing equation. It also assumes 60-degree temperature. It assumes a specific gravity of the gas of 0.6. It assumes that the piping configuration and schedule are not a factor, which obviously they can be. So it also doesn't tell you anything about noise. I mean, I could go on as to why you might want to still utilize Valspec, but that CG is a helpful comparator against other valves and also against the conditions you have to see if this particular valve will do it. Okay. Any questions about any of that so far? All right. So before we leave this, I was talking about this standard port to large port conversion business. Take a look at the row above it where it says standard single port and of course the 150 class flanged FG3. So if you have an FG3 in the field and it has 100% capacity plate, it has a CG of 1130. If you decide it's time to convert that over to large port and you're basically reusing the body, you do that and you don't change the capacity of the plate when you put the 2-inch large port on it, you've just boosted the capacity substantially. So one of the things that you could do, especially if it's a reg relief situation, is just step down the size of the throttle plate one capacity size, and you'll notice that that gets you, in this instant, it gets you exactly where you were. In every other case, it gets you very, very close. So it's a good way to look at a kind of a guide if you're not interested in that added capacity. Just when you convert it over, utilize the next lower step in throttle plate size. Okay, which gets me to the point I guess I started this with. Look at the FG3 again with a 35% plate. The CG's 380. Well, what do you do in an instant like that if you have that same scenario? Well, there is a 25% step drill hole plate. It's not listed on this chart. We have literally dozens of them, to be able to install on a valve that's needed for this application to be converted. And the 25% plate, the large port plate, has a CG of 379. So when you get this, you might want to make a note on it that that's an available option if you're trying to convert over a standard port that has a smaller capacity plate and you don't want that capacity. Okay, so let me know if you didn't get this, and I'll send it to you so you'll have it just as a nice friendly tool. All right, so we talked about the throttle plates. Then when I put that on, it sets my capacity. Then I decide my diaphragm. In our example here, I said 75, but let's talk about practical perspective of what my options are. Okay, so I have actually 5 options of flexible elements that I can pull from, and I may pick them based on the particulate or the composition of the gas. If I have H2S issues, that kind of thing, I may find that it's not doing a number on my nitrile, so I want to do something else. So there's a Viton option, and it includes all the O-rings as well. I can put all Viton in it. It has a nice soft 60 durometer diaphragm. It's very flexible, that will give good lift and low differential. So I'll pick that in an instant where I am going to use the flow grid, where I'm making a down to a 20-pound cut. I don't want to use a flow grid in a situation where I'm making less than a 20-pound cut normally. It's a better place for a Flomax when I'm making shallow pressure cuts, because they do extremely well in that arena, and they also can provide very high capacity, which, we're talking about 150 class sets where the inlet pressures are lower. It may keep you from having to use a 3-inch valve because of the fact that obviously with lower inlet pressures, less density in the gas, you may need bigger body size to get the capacity as you need. So Flomax may be the way you go there, but 60 durometer diaphragm when I'm making a 60-pound cut or less, down to about 20 pounds. Also, while I'm thinking of it, that's another reason why if I chose to use a flow grid as a relief, which is great relief, but I don't want to set it as a relief if my set point's going to be, under 20 pounds. That's the absolute minimum I want to use it for. And the reason we're saying this is there's a certain amount of differential pressure required to make sure that this gets, nice, good seal on the throttle plate. If there's any kind of particulate or wear on the diaphragm and those kind of things, we want to be able to press into that throttle plate and shut the gas off. So we, even with the added, help of that mainspring that's on top of there, we want to have good closing bias. And so we don't really want to get into the realm of, normally operating with a 10-pound cut. Will it be full open? In some instances, yes, it can go full open with 8 pounds. But it's also an issue of we want to reliably lock up and, its lifespan. So that's why we don't want to spec it that way. We'll use another valve. 75 durometer is the other version, or the next version. And it's good for basically 60 PSID all the way up to the maximum differential of a Mooney flow grid. A Mooney flow grid can make a single pressure cut of 800 PSID under normal conditions if it's a 2-inch valve or larger. And if it has a 1-inch throttling area, obviously with the appropriate flange connections to handle that kind of pressure, but it would be 1,000 PSI. So up to 1,000 pounds, I can have controlled across a single regulator, which of course would be a block of ice without other considerations, but it'll handle the pressure. So I'll just need to deal with Joule Thompson. If I have those higher pressures, I'm probably going to want to go to a more, wear resistant material, and they make two 80 durometer diaphragms that are very stiff and wear resistant. This is 80 high model, much stiffer than the 60 that I had in my hand before. With that extra pressure though, it's going to force it up off the plate just fine, and it's not going to wear so much with all that gas screaming below it. They have an 80 low model, 80L, which is a little less wear resistant than the 80H, but it stays flexible in colder temperatures. So it's kind of like picking a good model of Goodyear tires. You pick what features that best fit you. So I decide those things, and then I put the diaphragm that I want in there. And in every model from 2-inch on up, it needs just a little space for the diaphragm to lift up. So it has a spacer plate. Spacer plate simply provides that. So it envelops. There's an O-ring here to make sure the gas doesn't escape around the throttle plate and makes it go through it. And then I have a spacer plate that sits down. And then I have the diaphragm that I've selected that fits down tight on that spacer plate. A note, I guess, if you're trying to help your technicians in this particular body size, they may have some of those standard ports out there. They may still have rebuild kits and diaphragms that are standard port. Okay, that is going to cause a problem for them when they go to put in a standard port. This is what the standard port looks like. It's the same outer, how do I get these in view? The same outer surface area, but the pockets are smaller. So you can see that this, this one is bigger than this one, and they're labeled standard port on this one and also large port on this one. And they have, addition to that, you can see there's a little different material. The old standard port was made in a process that annealed the nylon and the rubber together, the buna together, in a way that it would get decompression sickness and start to bubble up and basically destroy itself. This has a process that helps to eliminate that. So in terms of let's say a scuba diver that goes to depth and is breathing air at 100 feet below the surface. Well, he has, an additional 3 atmospheres of pressure that concentrating the nitrogen in his breathing to the point where if he stays there for a while, that higher concentration of nitrogen is absorbed into his tissues. And when he decides to come to the surface, if he or she doesn't allow for sufficient time to off gas that absorbed nitrogen, it results in the little nitrogen bubble or little nitrogen gas particles joining together. As they find each other, they become bigger bubbles, and they can't get out of the tissues anymore. So they just tear their way out. So the diver gets the bends, it blocks, blood flow to the brain, all kinds of nasty things. And the only solution for that person is to rush them to a hospital where they have a recompression chamber and basically put them under pressure and force the bubbles to be small again. And very, very slowly over time, let those gas particles find their way out. Well, that's what's happening with
soft good components in natural gas where you get, you know, methane, get absorption into the material at these higher pressures, and they can live there forever, you know, until maintenance occurs. And when they're depressurized, they start to have this same situation. And this is kind of an example of what kind of thing you would see where it might have looked perfectly fine until the point where it sat there for a week, and then they put it back into service, and you know the diaphragm is ruined. So you know, talk about what kind of a plan that someone might have for doing maintenance in, you know, the situation where they have to go in and inspect these things. The manufacturer recommends that you inspect all the soft goods annually and then replace them as needed. So as they go in, they look for signs of excuse me, wear, or you know, things that look like they're becoming real stiff and kind of losing their flexibility. Whatever the case is, that will be the time that they can make a decision as to replacing them. And there'll be obviously company policies that trump that, where they would say, well, we've taken the time to open the valves anyway. We're just going to put a new rebuild kit in. I understand that. It's also the case in some places where you get the wear on one side of the diaphragm. While they're in there, they'll flip it over to the other and get a fresh side from now what was the inlet is now the outlet, to give them a fresh surface to throttle with. So, and then keep it going. The only issue, like I mentioned, is, and it doesn't happen so much in a 150 class set, because it's just going back to the diver example. If a diver is diving only to one additional atmosphere, 33 feet seawater, and he stays there, I don't know if he had like a diving bell or something, a week, a month, and then decided just to come to the surface, there wouldn't be any of that decompression sickness, because there's not enough concentration of nitrogen, even at complete saturation, to cause that kind of damage and problem. So usually in 150 class sets, you don't see this nearly as bad as when you're talking about, you know, the higher pressure. 600 class certainly is something where you see this more. So that newer style diaphragm will naturally help and give them more life, which is good. The standard ports, none of them had that G stamped information, and any diaphragm has the year, the date that it was made on it, and it also has that durometer information. So, you know, from the engineer's perspective, it's just, you know, what soft good components are the right for the job I'm speccing, and so that just gives you the information, the variety of options you have. The mainsprings are also a good part of this high rangeability and turn down, because it has that accordion style. And they do make a standard version. Do you see the low diff? And they make a low differential version. And it's like, you know, it's like, you know, just pick the size and they just go up in size. So this is a 4-inch low diff. We have a 6-inch standard mainspring. So, and of course there's also an 8-inch. In a flow grid, there's no throttle plates, soft goods, or mainsprings that are bigger than 8-inch. I know I mentioned that there were 10-inch and 12-inch valves, but what happens in those 10 and 12-inch valves is they are dual ports, and the 10-inch dual port has 2 6-inch throttling areas, and the 12-inch has 2 8-inch. So in those instances where you have those, obviously you're buying rebuild kits for both sides when you're doing your maintenance. You can control them with one pilot, or you can set them separately, such as you might have like the primary, secondary kind of runs, where one only opens if the other one isn't keeping up, kind of thing, if you wanted to set them up that way. But they're all just these same components. So why would you use a low diff mainspring, which is much more soft and flexible? This to me is in kind of, we've come to a unanimous agreement doing troubleshooting for people, is a little bit problematic. If you guys have dresser roots meters and you know, the subject has come up about, well, do I use a restricting orifice plate? Well, the job of the restricting orifice plate is to protect the meter. You know, it's to keep the meter from being overspun, because a positive displacement meter like that gets gas slammed through it really quickly, high demand load downstream, or somebody just opens the inlet really, really fast and tries to fill the downstream system through those impellers, they get overspun and lock up. So the solution is you put a restricting orifice plate downstream of the meter, which basically makes the gas have to get sucked through the hole of a straw, right? Can't get through there fast enough to direct the meter, but the downside is the loads that you're supporting are getting starved. So it's not typically a good solution. And the answer in that instance is get a bigger measurement chamber where the impellers can move slower and not going to be so subject to that, you know, in the max, you know, speed loading situation. Same thing with this low diff mainspring. The reason that it gets spec, some people want it, is because they are at that point where they're making a shallow cut and they want to get full lift of this. They want to get, you know, the ability with that lower difference between the inlet pressure trying to rise up and the pressure on the top. They want to get it lifted out of the way because they need that capacity. So they'll want this to basically let that diaphragm come up much easier. So that's kind of one of the reasons that they're looking to do that. But again, coming back to the meter example, because that can also, because it's add closing bias, it helps you to shut it off. Instead of having a lockup problem created by the fact that you need more capacity, either go with a bigger throttle plate or go with a bigger valve, so that you have the needed capacity even when it isn't giving you full lift, but then you have that added closing ability when it needs to lock up. And really, this only comes into play, you know, when you're talking about, you know, the 30 PSID or less situation anyway. But most of the time, it's just better to go with a 60 durometer, nice soft diaphragm, and stay with your standard mainspring. But, you know, you have that option. Okay, so that goes on. Once the mainspring is in, and it kind of goes just the direction of the, you know, the body, so that it's flexing on the inlet side, we finally set the direction of the valve. And this is nice because when you're speccing, let's say a dual run, primary and secondary, you know, run or a main run and a standby run, you notice that it has a loading port on one side. It has a directional arrow. You know, these things are made where a blind person could put them together, no problem, because everything is definitely got a place you can feel. When I put this down, it is going to set the direction of the valve. So if I flip it over, if I go this way to do my left-hand run, now this gets moved over to this position on the other side, and my filter goes on this port. So it gives everything the outboard access for the people that are maintaining them, commissioning them, etc. Simply by flipping the position of this throttle plate. Okay, that sets the direction. Okay, probably a good time to see if anybody has any questions about the flow grid that I haven't covered very well. While you're thinking about that, this style, because it's going to be different than the Flowmax we talk about later, is an unloading design of regulator. It has to unload gas off the top of this spring case in order to allow the valve to open. So it's normal state of being until this pilot tells it what to do, forces you know, this to open by dumping gas off, is basically closed. And so it's an unloading design. And in that design, having this restriction on the inlet side of the pilot gives it the ability, and also the rangeability of sensitivity, you know, on how it opens and how it closes. Okay, any questions?
Nothing so far.
Okay.
I've got a question.
All right.
Is there a like a rule of thumb for a minimum differential pressure for the flow grid?
Yes, I would say don't spec them if you're making a less than a 20-pound cut. And I really would like to say 30, but I know a lot of times that they work really well in that range of 20 to 30. We just got to put the right components in.
Okay, thank you.
And we're going to talk about the Flomax later, but that's where the Flomax basically shines, is in those low diff situations. So, you know, and also if you were looking for relief at 3 or higher pounds, that would be an option for you too, as a Flomax. Whereas with a flow grid, because you need that 20 PSID or more, I wouldn't set it as a relief or a back pressure valve unless I had that kind of differential. Okay. Let's talk then about basically sizing these then. If you want to, you can look at the link that we gave you, and we'll play with it on our end. And while Drew's getting that up, let me talk about the different things we can do with a flow grid. It can be a standalone regulator. It can do, you know, a series of cuts, you know, 2-stage, whatever, pressure cuts. It can be set as a worker monitor. It can be a working monitor where each regulator is making its own cut, but also is going to back up its other partner if for whatever reason that one can't maintain its pressure, can't maintain do its portion of the job. It'll be ready to make the whole cut. And then it can, like I said, be a back pressure valve. It can be set as a relief. It also can do flow control override on the pilot as an example. So all these things could be things we could play with in sizing. But to do flow control, obviously it needs something else besides these standard components that I mentioned, which were the body, the pilot, the restrictor. They have to be there. And then it's a choice as to how you do filtering and how you want the mounting. And we also do custom stuff. So like, I know this one that I had in front of me, when the picture comes back, you'll notice it doesn't have a Mooney filter on it at all. It has a Welker filter with a 4 micron filtering element. And the cartridge can have a material called sulfur gone in it. So it has, in this particular instance, it was necessary. You know, you get plaque buildup of H2S inside of the small spaces in a pilot. And over time, that starts creating a situation where, you know, the arterial system in the pilot starts closing up, and the downstream set points start dropping. And the technician sees it because he went out there and, you know, had to bump the pressure up from the month before or 2 months before. And then he comes back in, you know, a couple months and it's dropped again. And what's happening is the spaces in the orifice and the plug and stem are slowly closing in. Well, I can solve that problem by providing better filtration at the pilot level. So this one has a sulfur gun cartridge that basically is going to capture and eradicate that H2S and prevent it from being a particulate buildup inside the pilot, instead of it just being a 10 micron filter, general filtration to keep the trash out of those small spaces, because they'll come through a lot of times, especially with big pressure cuts. You know, you get particulate dropping out of the gas as the temperature drops. And so that particulate will glue itself in small particles on each other and on each other and on each other until it starts to become a problem. So filtration and heating are 2 ways to combat that. So the valve stays clean and needs less maintenance and does its job for, you know, that it's intended to do without as much cleaning. Okay, so back onto the Valspec. So let me ask you, is anybody not familiar with Size and Mooney with this program? Probably, hopefully someone is. Has anyone used it before? Okay, I'll assume.
A long time ago.
Okay, all right. So got someone who is familiar with it. Let me make everybody familiar with it. This will be a helpful tool in your tool belt. To use it for Mooney, and I have to get kind of closer so I can see. So when you first open it up, it's going to be set to things that you typically are not going to be using it for. It says flow control at the top, and it says for water. So let's start by making sure we've got the right family. Go into where it says item on the top, and see where it says Mooney Regulator. Pick that. Okay, so it changes the parameters when I pick the Mooney line and under item. And now it says at the top, you see fluid, the natural fluids is gas and natural gas. So I can change those things, obviously, if I need to do sizing here, but it's giving me those as defaults. You'll notice that looking down the right-hand column of the things that I'm going to fill in for process conditions, also, it says that the pressure is in PSI-A. So I think it's set up this way, you know, with an engineer in mind, where oftentimes you're designing something and the exact location, it may be multiple places you use it, so you don't know exactly what, you know, the elevation is going to be, how the impact of atmospheric pressure. So you can leave it at PSI-A, or you may have a design you're doing for a specific site and you want to use gauge, so you can pick gauge. One caveat there is, all it's doing when you say gauge here is adding 14.7 psi. So if you're not at sea level, then that's not good either. That's not right either. So you can actually just, you know, cheat it, you know, use PSIA and whatever the pressure is that that you have. You can take that atmospheric pressure away, and you'll have more of an exact look at what that is gauge wise. Anyway, so going to what we can do with it. You see, going over to the left on top, it says station type, and you can pick from some options. The single regulator, the regulator plus, can you slide that forward? Because my eyes are so bad, I'm having trouble reading it to them. Uh-oh. Or I can come forward to you. Okay, so single regulator, regulator plus relief, you know, your worker monitor, a worker monitor plus a relief. So those are the basic things you set up. The most important thing here really is if you're doing a single regulator or something that is working in series with another valve in line, because if you have any valves that are set in series, there's going to be some loss of capacity, as you could expect. Let's say a worker monitor, and you have, you know, the monitor set up front in that situation. Well, when it's full open, it's still not going to be like the pipe as far as letting the exact amount of inlet pressure through. There might be a slight drop in pressure that the second regulator feels. So there's always an accommodation made in the sizing if they're set like that together. And it'll take away a little bit additional, let's say, effective capacity, they call it. So, and if you're going to size a relief by itself, you could do it in the reg plus relief sizing, or you could simply just treat it like sizing a regulator, except that your downstream outlet pressure is atmosphere. So let's say your set point was going to be 30 pounds, and you were going to use it as a relief. You could use the sizing like it was a single regulator and just put the outlet pressure as atmosphere, and you're going to get the capacity that you're looking for, you know, as to what it can do as a relief. Okay, and then another option that I mentioned that you could do is a working monitor. If you were doing a working monitor, what I would select here is your regulator and standby monitor. But then when you get over to the categories to the far right, where you're actually setting in your process conditions, you would want to set one for, you know, the first stage, you know, that the front regulator is cutting to the interstage pressure. So you want to set those parameters in. You want to do a separate one for the second stage, and, you know, its job, its it's cut. And then you're going to want to do another one where you're planning for either one of those to protect because the other one failed to do its job. So you're wanting to do one that shows the whole cut. And, you know, you may do this a few times because you might have to also then consider various inlet pressures and also various flow rates. So, but you'll basically do it within the parameters of the, you know, the worker monitor scenario, okay? So we'll move down, let's just say, let's say regulator standby monitor. The next thing we do is we pick what piping we have, and let's say 2-inch here. We have to pick the schedule. We'll just say standard for now, but you can be more selective. You notice that since it's a worker monitor, it makes me select an interstage piping. Let's talk a little bit about the piping in or the arrangement of Mooney regulators that are doing worker monitor work. The vital thing, the most important thing to consider is the placement of the sense lines. The sense lines are going to give the pilots the opportunity to obviously understand what the pressure is they're trying to control. We don't want it in a place where there's a lot of turbulence. So we don't want it nearby a change in pipe direction, change in pipe size, other, you know, immediately upon the exit of another component that, you know, that exit of that component might be create turbulence. You know, if you had 25 pipe diameters, you would get back to laminar flow, but you know, the good thumb rule is 8 to 10 pipe diameters downstream of either the valve exit or wherever you place that other things that it's coming through, so that you got that kind of amount of straight pipe. The distance between the regulators and the worker monitor, since both sense lines are downstream of the second reg, is not all that critical. It's where you can, if you have a space constraint in your design, that's where you can make it up. You don't have to worry really about how close you get the two. I have seen situations where literally the outlet of one was butted up against the inlet of the other, and they worked fine. It's obviously nice to have a gauge there. You know, it's not a perfect scenario if you don't have any room, but it's better if you had to pick a place for room for that straight length of pipe, so the sense line, you know, placement could be better. So the interstage piping, they typically recommend that it be the same, you know, size as the inlet and outlet piping. So let's say you had 4-inch pipe, but you only need 2-inch Mooney regulators because they can more, you know, be more than handle the capacity. You know, the typical way that the design goes is that interstage will get stepped up to 4-inch and then step back down to 2-inch into the other body. That's another place where potentially you could compromise if it was just make it easier to get it in. But that's what they typically you'll see, is that those will all match: inlet, outlet, and interstage, same pipe size. Okay, and then once we pick that, we go down and select a valve. Let's pick some parameters before we do that, because you know, we could use a simplified gas sizing equation as an example just to get in the right ballpark. So let's say we've got 225 pounds on the inlet, and we're going to cut pressure to 150. So 225 in, 150 out, and we'll just say normal for now. Let's just do normal. The flow rate we'll pick will be 200, and we will say MCFH. So we can drop down and pick all these different options for flow. 200,000 cubic feet an hour will be the flow we're going to use. That's right.
Normal.
Yeah, just for now. Yeah.
200.
200. It's a max, but okay. So let's also change that PSI to PSIG, and then put in the 225. And then our outlet set point's gonna be 150. Can you guys see this? Is this working good for you?
Yes.
Okay,
Yeah,
excellent.
we can see.
Okay, and then you have the ability, if there's a different inlet temperature, let's say it's just coming out of, you know, a line heater or something, it's preheated. But normally, we, you know, the default here is 60, we'll just use 60 degrees Fahrenheit. You can pick Celsius or something else if you prefer. And then I can hit select valve. Oh, and back to the point about doing that first. Okay, so if I did that and using my simplified gas sizing equation, 200,000 divided by the inlet pressure, so Q max divided by 225, what does that give me? It's like 888, something like that, right?
Divided by
225.
Yep.
Okay, 88.9. So it's going to be in the realm, thinking back about that chart that I just talked about, where a 2-inch large port with 100% plate is at 1420 CG. So I know that if I'm going to be in the ballpark of 890, 900 required CG, that a 2-inch valve will work here. And since I have 200 pounds on the inlet, I'm just going to say, okay, well, this is a 150 class set. So I'm going to go into this select valve and I'm going to look for that. So I can go to the top and it says series, we'll do flow grid, size 2-inch, class 150, end connections, raised face flanged. Okay, and let's leave capacity all for now and apply the filter. So I got my options. All right, so let's just start out with the one that's first checked there where it says FG29100 and say okay. Okay, so it's placed that in as my first valve, either worker or monitor, doesn't matter. And then I can pick the plate stop. Normally it's going to be slotted. Remember, I typically in a 150 class set want to use slotted by virtue of the fact that if I don't need tremendous rangeability, I definitely want lockup. So I'm going to avoid those high turn down throttle plates if I don't have the differential pressure. Okay, and then the second one will just be a mirror image. So I'm going to select the same valve the same way. I can call them worker, I can call them monitor or whatever. If you have an SOP where the first valve picked is your upstream valve, then you could, you know, decide, you know, by your standards, which one you like to put as the worker and which one the monitor. Obviously, these could be switched at any time. If you want to give one a rest and make it, you know, make the other one work. But so now we can calculate because we've got valves to calculate against, and it populates the flow conditions. Okay, so you see that.
Jeff,
Yes.
would you check box the interstage pressure or not, or
If I'm going to do a working monitor, I definitely would be concerned with the interstage pressure. Okay.
we tend to do working monitors, so
Okay.
that would be
Okay. So going back to that earlier scenario, using this, like you're mentioning, using this same setup, because there is no working monitor option, you know, in the drop down or station type. When I go in and I'm actually saying, okay, well, I need to consider that these valves are both working, and also they're going to back up each other. I'm going to put an additional second pilot on the first regulator so it can look all the way downstream and see that the second regulator didn't do its job, so it'll make the first regulator do the whole cut. Or if the full inlet pressure comes through the first valve because it fails, then my second regulator will be doing the full cut. So it's in that time that I would be worried about interstage pressure. And you know, if you want to do that here, what would you like to see? Like, how would you like us to change what we're doing in here to accommodate what you're thinking? You have if this was 225 on the inlet and 150 out, do you want to make an interstage cut?
I don't know for sure how you would do it on this. So what would you
All right, well,
recommend?
hey, let's do that next. Let's do the working monitor scenario. But just finishing this one up then real quick, you can see looking at the flowing conditions that it's saying the calculated capacity of that particular pressure cup at that flow is 792.8. It recommends higher because it wants obviously a safety margin. Anytime we're dealing with Q max, you know, particularly if it's not a Q max that is CFM, you know, if it's not cubic feet per minute, then there tends to be in that maximum hour of flow, minutes of flow that are above that maximum average, right? So it could peak above that or drop below that, which forms that final maximum rate per hour. So we want to accommodate for that when we're doing valve sizing, and also, you know, we might calculate things based on what we anticipate is going to happen. But when it gets out there, there's actually less inlet pressure, and you know those peak winter periods at 7 in the morning in February, and there's less capacity because there's less inlet pressure. So we're going to provide about 20% safety margin on top of this, and not run the right up against the 100% capacity typically in a station estimation. Okay, so, and you can change that if you want though. If you go over to where it says station on the left side, I could change the capacity factor to 100 if I wanted. It's like I've got the exact information. I want to know the exact answer. I don't want a safety margin. You can put in that I want it to size to 100. And all that it'll do, quite frankly, is when you look over at the calculated CG versus the recommended, let's do that real quick. Calculate it again with 100. Okay, you notice they match. That's all it's doing. It's all it's done. It's like, well, it's still estimating that's the flow, but I'm going to get rid of the recommended additional 20% that I'm going to use for selecting my throttle plate in this case. Okay. All right. And so it's as simple as that as far as to get the information. And you can see some of the other things that you don't get from doing the simplified version. I can take a look at, you know, the exit velocity. I can look at the noise. I can look at the maximum flow rate that'll come through the valve, which is 253.3 MCFH, if I next have to consider the relief that I'm going to use to back it up, right? This set. So pretty good information. Also, outlet temperature. Am I going to get into a situation where I have icing? You'll get a warning at the bottom if you do, and then you can decide how you're going to, combat that. Catalytic heating, that type of thing. So, any questions before we move to another scenario, or is this helpful to you? I know we gotta give a second for people to dial in there.
Go ahead.
I was just going to say it is helpful. One of the things I was just talking to a coworker here, you know, Mooney used to have a calculator that they had, and it was kind of like this, and it would come up with the different Mooney regulators. This is awesome program, but I don't think any of us actually have it. I think for a long time it was only available, we had to go through the reps to be able to have them work the scenarios.
Yes. You know,
Is that right?
Yeah, you're right. So you know how corporations go, big companies go. So obviously Mooney had their way of doing things, and the designer Dick Mooney had a vision. At some point, they sold their product line to Dresser, and then several years later, after Dresser had acquired like Red Q and Grove and some other valve offerings to give a better suite of tools, General Electric purchased all this stuff for their gas and oil line from
dresser. And they made certain decisions to make it the GE way. And one was that they wanted everybody to come to their website where I guess they could see how people were sizing and what they were doing so they could collect their own information, and didn't want that out of their grasp. So that's the time frame you're talking about, okay? Well, since then, Baker Hughes has taken over the Mooney stuff, and they're, you know, they have a different philosophy. They're like, we want to get this out to the engineers and let them use it in their sizing. We see that as being a, you know, benefit to us financially, I'm sure. You know, that's probably part of their practical thinking, because if you can't fully evaluate them, then you're not going to be as likely to use them. So smartly, I think, they gave this access back to you. It's not to say that you can't use this as a resource anytime you ever want. I mean, we'd be happy to do sizing or discuss the, you know, the characteristics of the valve under certain conditions anytime. I mean, that's something that we enjoy doing, and we want you to get the right stuff. And we're going to be the ones that configure it anyway, because what we do is to create speed for you. So when you have anything from a planned station you're going to install to a gas emergency, you're going to get basically the same high, you know, rapid response from us, because we stock the bodies with throttle plates and diaphragms in them, obviously, but we stock hundreds of throttle plates and thousands of diaphragms, etc., and all the pilots in every configuration, all the restrictors, swage lock tubing to the hills, all the connectors, and our guys take the care and effort to configure these the way you exactly want them. So when you want a Welker filter on it or whatever the case is, that stuff is going to be basically done and out the door this week in a better way than it would come from Jacksonville. We used to just bring them in fully configured, and we were constantly, when we would go into the valves, finding from somebody who was just assembling them and somebody didn't catch them, with a pinched body O-ring or spacer O-ring, or a large Mooney valve that has a direction on the throttle plate, because the larger valves, 4-inch and up, the throttle plates at the step drill hole, there's only one side that's step drill hole, and the other side is just 100% slotted, and they would be in backwards, so that the whole advantage of the reduced capacity and the rangeability would be defeated by a knucklehead that assembled it. So we stopped that because that's the way we are with everything, and just started bringing it all in our house and doing it here. So when you order something and you say, I got to have something overnighted, it's going to be overnighted. You know, it's not going to be, it's going to be processed. Your order's going to be processed in 2 weeks. Then the clock will start. And if, by the way, if there's a problem, you know, you find that, you know, in the body that we didn't have to open because it had the right diaphragm and throttle plate, that the diaphragm got pinched, well, I'm going to get it to you that same day. I'm shipping you a new one out of my stock, and I'll deal with the manufacturer to get them to, you know, I have to submit a FERT, they call it, a field initiated request to identify the problem, and so they can evaluate why it happened, and it goes weeks and sometimes months before I'll see that O-ring back. But you're going to have it so you can keep flowing gas. So it's kind of, I don't know, I got off on a tangent there, but that's philosophy that goes with the sizing program and everything else that we do, that we like, that you have access to it. So.
Thank you. That was really good. Hey, I have another question before you go.
Yeah.
You have the min and the max, and you mentioned like your 200 could be a max, and would you ever be utilizing this whole thing to evaluate?
Yeah, let's say you knew that you had bin flow and you wanted to make sure that it you know, could support that. Well, I mean, by my throttle plate selection here, where I've got 100% capacity plate, the thumb rule I want you to know is, with 100% capacity slotted plate in any Mooney flow grid, you should plan on at least 50 to 1 turn down. If it goes to drill hole 100%, it's 100 to 1. If it's a reduced capacity slotted plate like that
50% that I showed you that had the welds on the back. That's 150 to 1 is its rated turn down. And if it has the step drill hole design where you got those nozzles close to the downstream edge, whichever side gets selected as downstream, it's in excess of 300 to 1, better than 300 to 1. So as I look at this, if I wanted to like really test that, it wouldn't give me a warning, which I wish it would, but I should, since I know I've got a 100% plate in, I'm going to start to lose a little bit of the low end control before this thing will tell me it will. So let's say I put in 1 MCFH. Well, 200 MCFH divided by 50 is not 1. That's a 200 to 1 turn down I'm testing here. But let's do it. Okay, so we'll put in 1, and we'll put in the same parameters. 225, the 150, and the 60-degree temp, and then we'll recalculate. Now it'll give me information for both sides. But if you go down to where it says percent travel, it'll give me now a number that says it's going to be open 0.348. Okay. What I would say in an instance like that is I might have to do certain things to make this give me better low flow if I had that 100% slotted plate in it. Probably I would, really have to do because, I've got, a little bit of flexibility here because I could always go to the 100 drill hole. I got enough differential pressure. I got at least 30 pounds. I could do that and double my rangeability. It's still going to say percent of travel is 0.39, but I know when that diaphragm starts to peak off of that center media and let gas flow over, it's only going to go in that first row of nozzles or first row of holes instead of access to those slots that aren't welded. So that's what's going to give me a lot better low flow control. And if I needed to get it, that's where I would get it. Okay, if I had room, I could step down to a 75 step drill hole plate, and then 0.3% open wouldn't even be working it out very hard, because the way that one would be designed, you'd have the smaller, the smaller nozzle holes for a few rows, a couple of rows before it ever even got to a full size hole. That help answer the question, or did I miss it?
Nope, that was great. Thanks.
Yep, no problem. Okay, so we had interest in doing a working monitor, and we can probably do it right here from where we're at. So let's just change the conditions a little bit. We'll probably change to 600 class valves because we're going to be making a bigger cut now. Let's use the same flow rate, max flow rate, and make now the inlet pressure 600 pounds. Okay, we can then have to decide, because we want to probably try to avoid icing. We're going to try to spread out that temperature and the pressure cut. Another consideration here with working monitors are, remember, the ultimate goal is I want one to be the exact backup for the other. So in a situation where I get 650 coming through and I'm trying to regulate 150, that both of them can do it equally well. The only way that both of them will be able to do it equally well is if they end up with the same throttle plate in it, right? So a lot of times the problem when designing a working monitor is people say, well, I always want to cut the overall total cut in half. But oftentimes when you have, less pressure because you're using that formula, as the interstage, you're driving the size of the valve or the size of the throttle plate and the second regulator up because there's less pressure for it to do the same capacity with. So it's more likely you'll be wanting to shade kind of toward your inlet pressure. Get rid of some of that pressure, some of that temperature drop, get that shared a little bit. If I spread these valves out a little bit, I can get a little rewarming and avoid the icing concerns potentially. Because I know I'm going to have them because I have more than a 400-pound cut being made here. And that's my thumb rule. I'm always thinking about 400 PSI because I know I'm going to lose 7 degrees with every 100 pounds of pressure cut for the Joule Thompson. And so if I'm starting at 60, 7 times 4 is 28. So 60 minus 28, I'm at freezing. So if I go below freezing, obviously, you know, and all the other things that go with it, like that particulate dropout, are going to be issues for me. So anyway, we'll share that. Let's just say instead of doing a, you know, like middle of the road where we're looking at taking that 450 and splitting it in half. Let's only cut like 150 to the interstage. So let's do we'll just say other. We'll use our other there and say max flow 200,000. The inlet pressure on this one, you just do 200 because it's already an MCFH, and then do 450, and then what we're doing here is 150. But remember too is on the monitor pilot, on the working monitor, the monitor has to be set above the second regulator's pilot so that it's out of the way and letting the first regulator make this interstage cut. So ultimately, when I consider that, the actual set point on the monitor pilot on that first regulator is going to end up being, I don't know, 155 or you know, between 150 and 160 somewhere. I don't want them so close that the two fight each other and I have my monitor pilot on the first regulator wanting to make the first one make the whole cut all the time. So I want it out of the way. And by the way, what's out of the way? That's a good question too, is well, what would be out of the way? Well, a Mooney pilot is capable of locking up or being accurate within 1 to 2% of its rated set point. I'm going to have a lot of say in what that is, whether it's 1 or 2, based on placement of my sense lines, the speed of the demand of the downstream load, is it a short run system, size of the sense lines. A lot of these things will affect how my pilot will know that pressure and will be able to make the valve respond to it. So if I want it to lock up tight, then there's things I can do just in the piping that will help that pilot, but the rating is 1 to 2%. So in a situation where, you know, we're talking about like 100-pound set point, that means I need to set the monitor like at least 3, you know, because it's gonna have like 1 or 2 pounds of error there. I need to have at least 3 pounds higher. And if it was 1,000 pounds, which we're not going to set with a Mooney pilot, I have to use a Becker pilot, but then it would be more like 10 or 20 pounds before I put my monitor set point in because of that variance. Okay, so just something to consider. All right, so we put 450 outlet pressure. We'll just say 150 for now in our sizing, 60 degrees, and then you can indicate the interstage and calculate. Okay, so now on this far right row, I'm getting a CG requirement on basically the total cut, but it has to make a full cut of the 416, only 416. I'm sorry, the second cut. I just did the second cut. Let's do the 600 to 450. We got to do that part of it too. Yeah, so 200, 600, and then the outlet 450. So we're showing how they'll share. Sorry, I messed that up. Okay, there we go. And then hit calculate. Okay, so if we're doing, and this is nice, this is what you want to see of those two right-hand columns. If I've done this right, the percent travel and the recommended capacity, they'll look like they're sharing it pretty well. You know what I'm saying? So obviously the 33% open, I could probably drop the size of the throttle plates here. I don't need to use hundreds, but and I also wouldn't be using FG29s, but if I picked FG31s or FG30s here where they had the different flange connections, it changes nothing about the sizing. I just have to be smart enough not to use a 150 class regulator in a 300 class scenario. So I pick FT30s here, but it won't change the sizing at all, okay? So that gives you kind of what I was talking about is where I shaded toward the inlet. I'm doing two things here. One is, you notice that in the normal category, which isn't normal, I know we're not, you can change those names up there, by the way, to anything you want. I dropped the temperature of the gas to 30, but when I'm doing this where I'm shading it, you know, from 600 to 450 and then 450 to 150, I've got a little bit of rewarming help going there. So it's gonna give me a little bit of assistance in keeping away from icing, even without a pilot heater. Okay, now notice the bottom, I got all kinds of warnings, right? So under these scenarios, I've got on the first couple where it dropped below 32, it's telling me I got icing, you know, I'm gonna have to deal with icing. And then also, it's telling me that on the inlet pressure exceeds the maximum pressure for the selected valve. Yes, because we put FT29s. So yeah, I guess it is helping us there. But it'll give you things that'll caution you to kind of go back and take a look at it. But that's basically how you would get going on working monitors setup.